Hello, welcome to this video. This is 1C.1 and we're going to talk about the binomial theorem. We're going to expand some binomials in this lesson. Our learning target is to learn how to use the binomial theorem in order to expand a binomial power. And some things that you have to be able to do first is you have to know and be able to create Pascal's triangle. We'll talk about what that is. And then we'll use the binomial theorem and Pascal's triangle to expand a binomial to a power. So before we go ahead and jump into the lesson on the binomial theorem, I want to brush you up on some of your exponent properties. The first one that you should be familiar with is the zero property, power of zero. Anything to the power of zero is 1. And again, the reasoning for this, if I take x to the power of 0, don't you guys agree 0 is the same thing as 1 minus 1? And now if I use a negative exponent property, isn't this x to the first over x to the first? And it could be anything. It could be like 2 minus 2. But the idea here is that x divided by x is 1. So anything to the power of 0 is 1. Remember that property. The other property that you need to know is the power of a product property. If I have a times b to the power of n, that's a to the n times b to the n. Now, you won't see it really like this, but something that you'll see is something like this. 3y squared. What a lot of people do is they'll just put the power 2 on the y, which is incorrect. And that's because 3y squared isn't that 3y times 3y, which gives us 9y squared. So the power of a product property just says you have a to the power of n times b to the power of n. Okay, so using these ideas, I want to go ahead and try some of these. I'll do the first example with you, and then these will be your practice ones that I'll have you go ahead and work through. But I want to simplify each of these expressions. So 3x to the power of 4. Again, using the power of a product, I'm going to apply that power to both the coefficient, 3 to the 4th, that's a 4, times x to the power of 4. 3 to the 4th, it's like 9 times 9, right? 3 squared times 3 squared. So this is 81, x to the power of 4. Okay, so go ahead, try these three, and then when I unpause the video, you'll see the answers here. All right, pause me now, try these. All right, so if you tried these for these examples, you should have gotten negative 2 cubed, which is negative 8, times y cubed, which is y cubed. Negative 4y squared, negative 4 squared, 16, y squared, y to the second. And then 5x to the power of 0, that 0 applies to both the 5 and the x. So this is 1, it's just 1. Okay, how'd you do? Good? All right, let's go ahead and look at the binomial theorem. We're going to go ahead and look at an expansion of x plus y to the power of n for several values of n, where n is a whole number. I have an example of x plus y to the power of 0, x plus y to the power of 1, x plus y to the power of 2, x plus y to the power of 3, and there are indicated expansions, right? So for example, if I took x plus y squared, which is x plus y times x plus y, this is the result of multiplying those two binomials. You would get x squared plus xy from distributing the x, and then you would get plus xy plus y squared from distributing the y. So that's the result, right? X squared plus 2xy plus y squared. I want you to take a second. I'm going to pause the video, or I want you to pause the video, and I want you to try to look at some patterns. What do you notice? Is there any patterns with all of these expansions? Okay, go ahead, pause the video, try to look for some patterns, jot down some notes, and we'll talk about it here. Okay, hopefully you took some time to look for some patterns, because pattern recognition is an important skill in mathematical thinking, so that's always important to develop. But we're going to talk about the binomial theorem and the characteristics that are exemplified and outline them above. The binomial theorem can be used to expand a binomial to a whole number power using the following characteristics. The number of terms in the expansion of x plus y to the power of n is 1 more than the power of n of the binomial. Or the binomial will have n plus 1 terms. So if you noticed, hey, its power of 0, it's going to have 1 term. Its power of 1, it's going to have 2 terms. Its power of 3, it's going to have 3 plus 1 terms, so 4 terms. That's the first item. Very good. Number 2, the powers of x are going to decrease by 1 as the powers of y increase by 1. So you'll notice that, and kind of this builds on the idea that your first term, if it's x plus y squared, your first term is going to be x squared, and your last term is going to be y squared. But notice the powers of x in between. So my powers of x are going to decrease 1. Now I have x to the first, and then I have y to the first. That's increasing. And then my last term, no x's, x to the power 0, and now I have y to the power 2. And it's more clear with x plus y to the power 3. X cubed, x squared, x, no x. No y, x or y to the first, y to the second, y to the third. Okay, so idea, x's go down, y's go up in terms of power. Number 3, the sum of the powers of each term is n. So if I add the powers up, it's going to be equal to the power. And that's kind of what I was talking about here. So power of 3, each term is going to have a power 3. So x cubed, look here, x squared, y to the first, x to the first, y to the second. So the sum will always be whatever n is. And then lastly, the coefficients. Did you pick up on the coefficients? The coefficients increase and then decrease in a symmetric pattern. There's a pattern to this, and that's called the binomial coefficients. Additionally, they can be arranged in a triangular pattern, and this is where Pascal's triangle comes into play. Pascal's triangle is named after the French mathematician Blaise Pascal, and this triangle, along with the characteristics, can be used to expand. So here is the first 3 rows. I guess they don't count the number 1 in the top. The first 3 rows of the Pascal's triangle. What patterns do you notice? And then, can you expand and find the next row? I challenge you. I'm going to pause video, see if you can notice a pattern, guess what that next row is, and fill it in. And I'll show you the answer here in a second. All right, so I'm actually live here with some students, but I challenged them the same thing. The most common representation that they showed in their work was this 1, 4, 4, 4, 1, which 4 out of the 5 is correct, but this middle term was missing. How the Pascal's triangle numbers are generated in the interior, it's actually a sum of the 2 numbers above them. So I have 1 plus 2 gives me 3, 2 plus 1 gives me 3. Here, 1 plus 3 gives me 4, 3 plus 1 gives me 4, and so this middle number is going to be 6. Yeah, 6. Okay. So they say complete the next 3 rows. Well, this next row, 1, 5, if I add these, right? And this next number comes directly from the power, right? So this is power 0, this is power 1, this is power 2, power 3, power 4, power 5. And then, so if I add 4 and 6, we would have 10, 6 plus 4, 10, and then 5. And then lastly 1. The whole idea here with Pascal's triangle is it's symmetrical. You could fold one half over onto the other, and you would have the same coefficients. Okay. So go ahead. I'm going to pause you right now. Complete that last row. Power of 6. Okay. So this is what you should have got for your next row. 1, 6, 15, 20, 15, 6, and then 1. That's the Pascal's triangle. Pretty cool, isn't it? All right, let's go ahead and look at our first example. The binomial theorem can be used to expand a binomial of the form a plus b to the power of n. Write the polynomial function f of x, which is equal to x plus 3 to the power of 4, in expanded form. So I'm going to keep the binomial here, and we're going to expand it with the binomial theorem. So I'm going to use colors. I'm going to use x to represent my my first term. I'm going to do this with red, and then 3 will be the second term, and I'm going to do this with 4. Okay, so if I want to go ahead and expand f of x, which is x plus 3 to the power of 4, this is going to be equal to, I'm going to put my coefficient. Okay, my coefficient is 1, and then I have x to the power of 4, and then we have 3 to the power of 0. Okay, your second term starts with the power of 0. plus, I'm going to go ahead and put my second coefficient. Remember, my second coefficient always matches the power, so 4 times my first term to the power of 3. Now it's decreasing, right? I started with 4, now it's power of 3. And then my second term is going to increase. So I had 3 to the power of 0. It is now 3 to the power of 1. Plus, okay, my next number in Pascal's triangle was 6. And now I'm going to put x. Remember, this decreases by 1, so it's x to the power of 2. And then 3 to the power of 2. Next term, plus, okay, and remember Pascal's triangle, the coefficients are symmetrical. So I have 1, 4, 6, and now I'm going to go back down. So 4, again, my first term is going to decrease in power, so x to the first, and then 3 to the second, plus, and then lastly we have 1. I'm going to have my first term, x, now to the power of 0. It's going to end up disappearing, or it's going to turn into 1, which gets absorbed. Not y, but 3 to the power of 4. And I think I have a typo here. This should be a 3 right here. Okay? All right. So now I'm going to go ahead and expand it. All right, so this part, you're going to have some computations that you're going to have to generate. But I have 1 times x to the 4th times 3. Again, this just turns into a 1. So I have x to the power of 4 plus 4x cubed times 3. So 4 times 3 is 12. I have 12x cubed plus, now I have 6x squared times 3 squared. That's 9. So 6x squared times 9 gives us 54x squared. Plus, I have 4 times x times 3 cubed. 3 cubed is 27. And 27 times 4 gives us, I believe, 108, 108x. Plus 3 to the 4th, which is 81, times 1 times 1. So we get just 81. Okay. Here is the expansion of our x plus 3 to the power 4 using binomial expansion. If you did not use this, what you would have to do is you'd have to do this. X plus 3 times x plus 3 times x plus 3 times x plus 3. And that can be a lot. Okay? All right, let's look at a second example. All right, example 2. The binomial theorem can be used to expand x minus 3y to the 5th. Write the expanded binomial. It's important to note that my second term here is negative. So again, my first term is x, and now my second term is negative 3y. So whenever I increase the powers on my second term, you're going to see parentheses around that negative 3y. So let's go ahead and let's look at this example. X minus 3y to the power of 5. So again, coefficient, the first one's 1, times my first term, x to the power of 5, times negative 3y to the power of 0. So I'm just taking my second term and I'm raising that to the power of 0. Plus, now I have 5 as my next coefficient, okay, times x to the 4th, times negative 3y to the first. Plus, I believe is it 10? Let me double check. Yeah, 10. 1, 5, 10, 10, 5, 1. So if you ever forget, you can check back in notes, or you can just quickly generate this triangle, which doesn't take too long. Might sound like a pain in the neck, but it's not too bad. 10 x to the power of 3, and then we have negative 3y to the power of 2. Okay, plus 10 x to the power of 2, negative 3y to the power of 3. Okay, plus, try not to run out of room, 5x to the power of 1, now negative 3y to the power of 4. If you ever forget what power on, remember your first term powers are going to decrease, your second term the powers are going to increase, and they should always total the total power. So it's power of 5, so this should equal 5. Okay, and then the last one, I have plus 1. Again, this is going to be x to the power of 0. Kind of trivial writing that. It's going to go away. Times negative 3y to the power of 5. And there's your expansion. Okay? So, now comes the fun part. We're going to go ahead and multiply all of this out. So, I have x to the 5th is my first term. I have 5 times negative 3. So this is negative 15, x to the 4th, y to the power of 1. Again, I get the 15 from multiplying 5 times negative 3. So that's where I get that. Then I have here 10 times x cubed times 9y squared. So this ends up giving us 90 x cubed y squared. Okay, plus next term, 10 times x squared times negative 27 y cubed. So this gives us a minus 270 x squared y cubed. Next one, 5 times negative 3y to the 4th. That is 81 y to the 4th. So this gives us 405. 405 x y to the 4th. Plus, lastly, we have negative 3y to the 5th. That's a negative 243 y to the power of 5. Okay, so there is your expansion. Okay, I want you to go ahead and pause the video. I want you to try this expansion, x plus 2 to the 5th, and then I'll show you the answers here in a second. All right, here is the expansion for x plus 2 to the power of 5. A couple of questions I get with students is, where do you get the coefficients from? The 1, 5, 10, 10, 5, 1. Remember, these coefficients come from your Pascal's triangle. They're the numbers that we talked about up here, right? So if I have a x plus whatever, or any binomial raised to the power of 5, I'm going to use this as my coefficients. 1, 5, 10, 10, 5, 1. The next example is something to the power of 4. Well, you're going to use this row, 1, 4, 6, 4, 1 as your coefficients. Again, notice on your expansion here that you should always start with your first term to the power that's being raised, and your second term to the power of 0. And then as you progress, notice in red here the powers are going to decrease by 1. 5, 4, 3, 2, 1, 0. And the powers here in blue for my second term are going to increase. 0, 1, 2, 3, 4, 5. And then they should always add up to the total power 2. 0 plus 5, 5. 1 plus 4, 5. 2 plus 3, 5. So on and so forth. Your final answer here, you should have gotten x to the 5th plus 10x to the 4th plus 40x cubed plus 80x squared plus 80x plus 32. Did you get it? Good job. All right. Okay. We're a little low on time, so here's what I want to do. I want to go ahead, I'm going to give you another example, and then I'll track back for the 2 practice problems. I'm going to go ahead and I'm going to expand here 2x minus 3 to the power of 4. So I'm going to go ahead, I'm going to expand here. I have my my first term, so 1 times my first term, 2x to the power of 4, times the second term, which is negative 3 to the power of 0, plus my next coefficient, 4, again times my first term, 2x, now 1 power lower, times my second term, negative 3, 1 power higher, which is 1. Plus 6 is the next term in Pascal's triangle, times my first term, 2x to the power of 2, times my second term, negative 3, to the power of 2. Plus 4 times my first term, again, 2x to the power of 1, times my second term, negative 3 to the power of 2. No, to the power of 3. Plus my last term, 1 times 2x to the power of 0. Again, that's going to go away, times my last term, negative 3 to the power of 4. Okay, and so now I just need to go ahead and compute these. So we should get 2 to the fourth is 16 times negative 3. So this is going to give us what? Negative 48 x to the fourth. Okay. Plus 4 times 2x cubed. This is going to give us 8x cubed times negative 3, which gives us, is that 96? Plus 96 x cubed. Okay. Plus, now I have 6 times 2x squared, so that's 6 times 4x squared times 9. Okay. And 6 times 4 is 24 times 9, 216. 216 x squared. This 96 should be negative too, because you have a negative 3 here. So negative 96. Plus, now 4 times 2 gives us 8 times negative 3 cubed is negative 27. Negative 27 times 8 is also 216, again negative. And then lastly, 1 times 1 times 81 just gives us 81. Okay, and then there is our expansion. All right, now I want to go ahead and look at a couple of these practice problems. Here is the binomial theorem used to expand x minus 2y to the power of 4. Please pause the video and try this example. And here's what you should have gotten. Notice the structure of your coefficients, 1, 4, 6, 4, 1. And then your x power should be decreasing, 4, 3, 2, 1, 0, with your second term, which is negative 2y, increasing from 0, 0, 1, 2, 3, 4. Now when you multiply all of this out, here's your final answer, x to the fourth minus 8x cubed y plus 24x squared y squared minus 32xy cubed plus 16y to the fourth. Maybe you've noticed by now, when you have subtraction in your binomials, when you expand, you're going to have alternating terms. Positive, negative, positive, negative, positive, so on and so forth. Okay, let's go ahead and look at the last practice problem I have for you. Please go ahead, pause me, try this example. All right, and here is the expansion that you should have gotten. 243x to the fifth minus 405x to the fourth times y plus 90x cubed times y to the second minus 90x squared times y cubed plus 15xy to the fourth minus y to the fifth. Hopefully in this video you learned how to expand binomials using the binomial theorem in Pascal's triangle. Give me a thumbs up, like the video. See you in the next video.